different variations, attentions, transformers, etc. So this is the plan of what I plan to cover in the next 2 or so weeks. So if you have any specific comments or suggestions, please feel free to let me know. And before I start the class, if there are any other topic that you wish to discuss, so please let us know. So any concern? Otherwise, I'll get started. Okay, is my slide visible?
Yes, ma'am.
Yes, ma'am.
Oh,
Yes, ma'am.
thank you. So, before I start with the some architectures of neural networks, I will, start briefly with some introduction to language processing, especially how we represent language, different components of the language, because this will be useful later on. And so natural, you must have in the earlier weeks, you must have looked at examples from computer vision. Have you? Have you looked at applications of CNN, etc., to computer vision in this class?
Yes, ma'am.
So we will take some examples from natural language processing. Before that, a brief introduction. Language is very important for us. It is the vehicle through which we try to understand, try to transmit our thoughts, express thoughts, think about complex things. And in the context of learning is typically data-driven. You learn from data and experience. And a lot of the data which is available is not in structured table, but in the form of natural language text or speech or images and videos. So this unstructured information form the vast majority of the amount of data available, and understanding these data is extremely important. So that is why understanding and being able to analyze natural language is very important. In this context, natural language processing is about building computational systems that can analyze natural language. What is natural language? What is natural about natural language? Can you tell me?
It's the language which human talks, in which way human talks.
Which has evolved with humans, which humans not only talk, it has evolved by human usage. It is in contrast to non-natural languages. So what languages are not natural? Can you give an example?
Programming languages.
A programming language. Humans use programming language. You use programming language to write programs, but they have been formally defined. They have not evolved in nature. So, and because the programming languages or logical languages, they have been formally defined, they have very precise syntax and semantics, and there are very standard ways in which you can analyze them. So natural language processing is about analyzing human language. And it has a lot of use cases. You want to be able to communicate with machines in your own language. And also you want machines to understand what you have written of them. And natural language processing has several components. And typically we can break it up into analysis, which is about understanding language by the machine and representing it in a form through which they can reason or do some task with the language. So representation is extremely important. When you say that the machine, we don't think that the machines have consciousness. So what do we mean by machines being able to analyze language? They should be able to put it into a representation with which they can do other downstream tasks. On the other hand, generation is about going from the machine representation to the, to the utterance of the language, to generating the language. And related to this is acquisition. This is very important in the context of machine learning because you want to have the ability to represent and have algorithms to acquire knowledge and data. So these are the three components of work on natural language processing. And in many natural language processing applications, we are interested about a language model, which is a model of language. A language model is a model of language. For example, a specific type of language model could be trying to understand or trying to find the probability distribution of a word in a particular position given the previous words. Words are some component of language, atomic components. I will not say it's completely atomic. So words are some of the basic components of language. And we have sequences of words to form sentences and sequences of sentences to form documents. And you want to be, if you have a model of the language, if you take out a word, if you remove a word or mask a word, you should be able to predict the word, or you should be able to find out what is the distribution of words that are in that position. And in order to do that, we have to find representation of words and also representation of sentences or documents, etc. So in today's class, first we will talk about a simple method, a simple but extremely powerful method for being able to represent a word. Now, in this context, we'll just, know you have been doing this course and you know that when you have deep learning, deep neural networks with multiple layers, they have many parameters. And if you have to train these parameters, it works well when you have quite a bit of data. Unless you have a lot of data, you cannot train the many parameters which are there in the network. Now, so the challenge is in many cases to get labeled data. If you want to be able to use deep learning on a particular task, you need labeled data. So one of the workaround through this problem is to have some tasks where you can use unlabeled data to learn something. And if you think about natural language text, there's plenty of text available out there. There's plenty of text in books, in web pages, in materials, and there's so many things. In Wikipedia, there is plenty of news, plenty of text there. But if you have to annotate them, that is a very time, that takes a lot of time, a lot of effort, expensive, etc. But can you learn useful things from unlabeled text? That is the question that we are going to answer. And we will see in today and in subsequent classes that what you can learn from just unlabeled text can give you a lot of power in solving various NLP tasks. So what we want to do is that take data in different forms of text, and you want to learn a representation. And using the representation, you can try to use it in various tasks. For example, English to Spanish translation. This is just an example, but you can use this representation for various tasks. And for this representation, we can have this representation at different levels. We can have representation of word or embedding of word. That is what I will talk about today. You can also have embeddings of sentences, etc., which we will talk about subsequently. Now, what this gives us, we will try to be able to use unlabeled text to get language models which are pre-trained on this unlabeled text. And these language models capture a lot of information about language, which can be used for different tasks. So with this brief introduction, let us get to the actual task. we want to be able to represent words. So take a particular language, let us say you take Hindi, right? So can you give me a rough estimate about the number of words in Hindi? The total number of words in Hindi? Anybody? So please, guess something.
Lakh, commonly used words. Around a lakh and
A lakh, 100,000, maybe. Good. Any other estimate? Do you agree?
Ma'am, we can create n number of words with any language, but meaningful, are you asking about the meaningful words?
Yes, the words in Hindi, words that you would use in Hindi, or words that will appear in a Hindi corpus, Hindi documents. Suppose you take all the Hindi news document archives or Wikipedia archives or Hindi books. If you take all the unique words which occur there, what is a good estimate?
Around 1.5 lakh.
1.5
Lakh.
lakh. So yeah, that's the order of 1 lakh. Yeah. So both of you agree. Yeah, I think it's a good estimate. Of course, this number depends on what you count as words, and it also depends on how large a corpus you are taking. You see, a lot of NLP is corpus driven. Studies is corpus driven. So if you take a very large corpus and you find the unique words, I think 100,000 is a good estimate in all that order.
Okay. Excuse me, ma'am.
Yeah.
Yeah, ma'am. What is the meaning of corpus? Like, what is corpus?
Corpus is a collection of documents, collection of text.
Okay. Okay.
It's a collection of items, documents that you have containing text. It could be it could be any type of document, right?
Okay.
So corpus and corpora are terms that we frequently use when talking about, because when we work with machine learning and deep learning, we work with huge collections. So the collections are called corpus. Now, suppose we have 100,000 words. Again, it could be 100,000 or 20,000 or 40,000, depending on what you consider as words. But whatever it is, suppose you want to now represent the words, right? Now, you must have seen a dictionary. You must have used a dictionary. I mean, of course, you have used a dictionary, right? So in a dictionary, what you have is that you have the words, right? And you have the words in alphabetical order. Okay, this is word 1, this is word 2, this is word 3, this is word 4. So what you can do is that, suppose you have a V number of words, V is the vocabulary of the language. So you can create a vector having V positions. And you can say the ith word in the list will have 1 in position I and 0 in all other positions. So this is called a one-hot representation. So if you consider each word as a separate word, not related to any other word, then the most obvious representation is to have an index for a word. And if you want to represent by a vector, you will get a one-hot vector, where for the ith word, the ith position is 1 and the rest is 0. Is this okay?
yes, sir. The size will be huge.
Size will be V, which is the total number of distinct words. The size of the vector is the number of words. So if there is 1 lakh words, the size of the vector will be 100,000. If there are 20,000 words, size of the vector will be 20,000. Okay. Now, this is the typical representation if you consider every word as a distinct individual entry. Now, what are some of the things that this representation cannot capture? If you use a one-hot representation, what can it not capture?
The
Count,
correlation
ma'am.
among other words. Correlation among other words. Like if a word is connected to another word, we can't represent them in the
Can you
one.
give an example of two words which are connected?
Like we are walking in we are walking. So here we and walking are two different words which are connected to with each other, but in one hot encoding it will not be represented.
So we and walking are two words, but we can be the subject of walking. Is that what you're saying?
Yes, yes.
Right. So you can say that some connection between word verb occurs with word subject. Right?
Exactly.
That could be one connection. What are some of the other connections that you can think of?
Like
Meaning.
emotions.
Hmm?
Emotions like angry, sad.
Yeah, give
These
an
are
example.
uh, mm, like due to failure, I feel sad. In here, failure and sad, they are two things which are
Right.
correlated.
So these words are somehow related to each other. But some other example, different type of example of how words are related or similar. Somebody else can give?
Synonyms and antonyms.
Yes, synonyms or antonyms. Give some example.
Like happiness and joy, happy joy, like
Happiness and joy.
the other will
These
be
are two words
and
which have similar meanings. However, their vectors does not indicate that their meanings are similar. Or let's say apple and orange, they have a similar role. So you can eat apple, you can eat orange, etc. Right? They occur in similar context. Right? Or even antonyms. You're happy or sad. They have some relationship. So this type of relationship is not captured, or no relationship is captured in this representation. Okay. So that is one problem. The other problem is the vector size is also very big. And so one is that the vector size is very large. Secondly, each word is different from everyone. So we want to, ideally we would like a representation so that similar words will have similar representation. Or if a word has some relationship with another word, that relationship, whether it can be captured by this representation. This is what we will ideally like. For an example, suppose, these are some words and we would like, and suppose we have a two-dimensional vector to represent the word. We would like that the vector for apple, orange, and banana. Just a minute. I'll just take one. Just wait a minute. Sorry, I'm back. So what we see is that these words, apple, orange, and banana, we want that their vectors will be close by. Similarly for bus, train, and car, and maybe juice and milk, etc. So this isn't something which we would like, is that words which have similarity must somehow have similar places where they are represented. And
Excuse me, ma'am.
Yeah.
Ma'am, does that mean that we are classifying the words into different classes?
We are not yet classifying. We are saying ideally what we want is that words which are similar, their vectors must have some relationship to each other. Maybe they should be close to each other.
By the rules of the language?
Not by the rules. This is what I'm saying, that this is the expectation. How I will talk about.
Oh, okay.
So we have no rules. We have just the use of language. We have just collections of documents, and we want to come up with some representation of words as vectors so that words which are similar, what is similar we will define. Words which are similar, their vectors will be similar or will be close to each other. This is a wish that we have.
Yes, ma'am.
Okay. Now, what do we mean by similarity? Now, we take this principle which was articulated in 1957 by this person called Firth. You shall know a word by the company it keeps. Now, suppose, some of you may be reading a lot, right? A lot of books. I'm sure that few of you are there, or many of you are there who read a lot. So, when you read books, it is possible that you come across some new word, which you do not know the meaning. You have not encountered the word before. Okay? So you come up with some word which you have not encountered before, and you keep encountering that word in that document or in other documents. Has it happened to you that you come across a word whose meaning you do not know?
Yes.
So what do you do? If you come across a word whose meaning you do not know, what do you do?
Contextual, like you try to understand the context and try to predict like what
So
would
you
be.
might want to open a dictionary, right? Which is what we would do when we were small. Or you might go to the web and find out. Or sometimes you will not bother, you'll keep reading the book. And after you have seen many places where that word is used, you will form an idea about the word. Do you agree?
Yes, ma'am.
By looking at how the word is used, you will form an idea. So, for example, suppose you have this word banking, and you look at different places where this word is used. That gives you an idea about that word. We can use this idea to say that this word is represented by its context, or from its context we can find its representation. For example, suppose this is a word dog, and you have come across many places. Of course, dog is a common word, but suppose instead of dog you have another word called pero, which you do not know what it is, but you look at the context where the word has occurred. So you will form a good idea about the word, and we want that, so this context will help to find the representation of the word. Okay. Now, suppose you take another word like cat. Now, cat and dog are different, but maybe some of the contexts are similar. For example, in the first document, you could replace dog and cat. Maybe in the second one you cannot do because a cat does not bark, but a cat mews, and maybe mews and bark are similar, right? Maybe you can replace this dog by cat. So it could be that some of the context of dog and some of the context of cat is similar. And if you use the context to find the representation, they may end up with similar representation. So what we do is that, so we have for every word, we have a vector which represents the word. We have a vector, and suppose this vector is a, say, 100-dimensional vector or 300-dimensional vector. And we are not restricting to a vector of 0 and 1, but the vector can have any real value. Right? So we have a real valued vector, dense vector, and every word has a vector. Initially, we can randomly initialize the vectors if we wish. Now, what we want is we take, the document, and we take each word in the document. We do it for every mention in the document. For each word in the document, we want that we want to, train the vector so that it is related to the vector of the neighboring words. So we can define a neighborhood. For example, we can define the neighborhood to be k words before and k words after this position. And then there are two ways in which we can formulate a problem. We can say that we want to find out, given the center word, what are the possible context words. We can either formulate the problem like that, or we can say what is, given a context word or given the context words, what is the most probable center word, right? So for example, suppose C denotes the center word and O denotes the context word. Suppose we take 2 words before and 2 words after as the context. So for each center word, there are 4 context words. Now we want to find these vectors such that we can find out the probability of O given C. So probability of O given C will be highest for a given C, given context word C, it will be highest for these 4 contexts. Okay. So I'm repeating, we want to come up with a representation of each word so that we can, given the central word, we can predict the, we can find, if you try to predict which are the context words which are most probable, the actual context words will have the highest probability. Is this okay? Have you understood? Please respond.
Ma'am, can you repeat the last line?
So we want to train the representations such that given the vector of our central word, we can now predict the vectors of, we can now predict the context words. Right? So given a central word, suppose there are V words in my language, V can be 100,000. So we find the probability for each of these V words. Right? Given the central word, we can find the probability of each of these 100,000 words. And we want that for those 4 words which are actually in the context, these probabilities should be the highest.
Got it, ma'am. Got it.
So this is our wish. Now, based on this, we will formulate an objective, which is summation over all central words. If we have a corpus, which is a collection of document, we take every mention of the word in the corpus. For every word, there are 4 neighboring words, and we want those probabilities to be high, and we want to sum it, and we want, so probability high means, because probability is a positive number between 0 and 1, this means the log of probability is also high. So we want to take the summation of the log of these probabilities. So this is my object optimization objective, and we want to have learned the vectors so that this objective is maximized. Okay. We'll come back to this. This is the basic idea. Okay. Now, based on this, we formulate 2 different problems. We can work on any of them, right? These are 2 alternative formulations. So the first formulation is called the C-bow formulation, where we take as input at the context word and we want to predict the central word. So given the context word, we want to project to the central word. That is, we want to get the probability of word given the context should be high for each word in the corpus that we are using for training. This is the C-bow formulation. Is this okay? Is this clear, the C-bow
Yes, ma'am.
formulation? Say yes or no. I cannot see you. At least I should hear you.
Hello, ma'am.
Yeah.
Ma'am, like the conditional probability out here says that the P of word given context, right, ma'am? Like context is basically what I have understood is it is basically the feeling of a sentence, right, ma'am? Like what is the sentence trying to say? Like how can we
context
quantify
is
that?
the neighboring words. So as we said that the meaning of a word can be derived from the context of its use. And what is the context? It is the neighboring words.
Oh,
Okay.
okay.
We do not know, we
Okay.
have computer. Computer doesn't know the meaning.
Okay.
Right? A computer is trying to find the vector of a word based on the vectors of the words in its context. And then we would want to, maximize this probability for all words in the corpus. So this is one formulation. An alternative formulation is where, given the input word, you want to predict the context words. Right? So given the input, you want to predict the context. So given the context, you want to predict the output. These are two formulations. You can use any one of them. Is it okay? Now, let's take only one of these and proceed. Let us take the CBOW formulation. And we make, certain, some small tricks to make the problem simpler and faster. First of all, we can, in this formulation, we are, say, looking at exactly the word in the -2 position, -1 position, +1 position, +2 position. Now, in order to simplify the problem, we can get rid of the word order. So we can just say that given this context word, you want to predict the central word. Given this context word, so you can look at this collection of words or each word individually. Okay? And if you want, you can convert it into a binary problem. So you say that these are 4 examples of data that we have. For each of the context word, we have to predict the center word separately. Right? So this is a simplification to make the process faster. Now in CBOW, we can, so what we can do is that because we are removing the ordering, we can take these 4 vectors and let us say we can take the sum of these vectors, right? And from the sum, we can project to the central word. So we can take the sum and we remove the word order, but from the vector sum, we try to deduce the central word. This is the formulation. So let us take an example. Suppose this is a sentence, the cat sat on floor. This is my sentence. And suppose I'm now focusing on this word sat. So these are the 4 context words, the cat on floor. We don't look at the order. And we have the vector of the cat on floor. And we want to take the sum and then project it to get the word sat. Now, this is how we will do. First, to simplify it further, we are taking one word to the left and one word to the right, just to illustrate. So we have these 2 words, which are the context words, cat on, and the central word is sat. So initially, we know that the cat is the second word and the on is the 4th word. So we can use the one hot representation of cat and one hot representation of on to start with. Now, we want to be able to project it. Suppose each of these inputs are n or v dimension. So initially, we have a one hot vector of v dimension. We want to project it to a n dimensional vector. So v can be 100,000, n can be 100. Okay. And when it gets projected, you have a neural network where each element here, each of these v elements is connected to each of these n elements. So the number of parameters are v cross n. Okay. And because in this one hot vector, rest of the positions are 0, only one position is 1, only this corresponding row in this matrix of vectors will give you the projection of cat onto the hidden layer. Right? So the connections, the n connections connecting this position to the next layer, that gives us a representation of cat as an n-dimensional vector. Similarly, the connection of fourth position to the n-dimensional vector gives us the vector of on. Okay. So we have V words. Each of them are represented by n-dimensional vector, and these vector comes from the weights which are in this connections. Okay. Now these two vectors are added, and from that now we again have a n cross V matrix where each of these positions is connected to each of the V words positions. Now, so for each position we will get a score. So if we take this summation, we will get a score for each of these positions. Now tell me if you have
score
understood.
as in probability of each position.
We'll come to the probability.
Okay.
First of all, we will just get a score. You know, if we look at this, suppose we have a vector here. Suppose the vector is 0.1, 0.3, 0.2, So if we multiply the weights connecting this to this, right? We will first get the summation.
Yes, ma'am.
Okay, we'll first get the summation. We cannot immediately get the probability. We'll first get the summation, which is a score. And ideally, we want that the correct word should have high score. Okay.
Yes, ma'am.
Anybody else has any questions? Please ask. Okay. So let us proceed. So as we have said, we have a parameter matrix here of size V cross N. This and this are actually the same matrix, right? And the ith row can be interpreted as the vector of the ith word. We have another parameter matrix N cross V. So in fact, we could have used this matrix also to get the representation of the word, but conventionally we use this. Okay. So we have two parameter matrices, W, V cross N, and this is N cross V. Okay. And these are the parameters that we have to learn. So as we said that the second row will give me the vector of the word cat, and the fourth row will give the vector of on, and then we sum them, and if we want we can divide by 2. So this is the summation that we get. Okay. So W transpose V cross N into this one hot vector of cat will give us the vector of cat. Okay. And then after we have got this, then we will get the score first. And now, as you have said, we will first, when we get these projections, we will get the score. These score, we have to now convert to a probability distribution. Right? So in a neural unit, first you get a, so far there is nothing no new. This is just a linear projection. From here to here, we get a linear projection. From here to here, we get a linear projection. Okay? Simple linear projection. And then for each position, we get a score. We get a score for each of the V positions. Now these scores, we want to convert to a probability distribution because we want to normalize it. And to convert, we use a function called softmax. So have you come across this function softmax?
Yes, ma'am. Yes, ma'am.
Good. So this is basically a V class classification problem. And these scores we convert to softmax. And if we use the softmax, that is, we take, on the numerator, we take e to the power the score. We take in the denominator, we take summation of e to the power scores of all the other positions. So now we get a V-dimensional vector, which can be interpreted as a probability distribution. So now, so this is the ideal, ideally this should be the word. And in this position, suppose we get a vector 0.7. Ideally what we want that this vector should be 1, this position should be 1, everything else should be 0. This is the ideal probability distribution. What you might get is a distribution where this has some value and the other positions have some other value. Okay. So what we want to see is that log of this probability, this position, this should be maximized. Okay, so we want this to be maximized. We want this to be as high as possible. Okay. So typically we take from W, we get the word representations. So now what we are doing is that we are trying to train this W and W prime so that from the context word we can get high probability of the central word. Based on that we learn W and W prime. Right? So that is about the Seabow model. We also have another similar model, which is an alternative model called the skip-gram model. It's exactly the same, but here the input is the central word and the output are the context words. And for efficiency, we can remove the word order. In fact, you can even convert it into binary problem. That suppose you have this, text segment, and this is your central word. And you want for this central word, these 4 are the positive context words. Okay. Given representation as central word, level as its context word is a positive example. Representation of is a positive example. Representation from is a positive example. Representation data is a positive example. And the rest of the V-4 words, representation X, where X is any of the V-4 words, these are negative examples, right? So from these positive and negative examples, we can pose the learning problem. And because for every mention we are getting V scores, it may take a long time to train because we want to train on a very large corpus many number of times. So we can do negative sampling. Out of the V-4 negative possibilities, we do not use all of them, we only use some. So, those things we need not talk about today. But basically what we have is this input is the central word, and then using this W matrix, which we are going to learn, we project it to this n-dimensional vector. And from this n-dimensional vector, we get the probability of a particular word position. If it is a positive example, I want it close to 1. After taking the score, of course, we do softmax. This is the softmax formula. So if this is a positive example, I want this probability to be close to 1. And we, if it is not close to 1, we take the log of that and we want to maximize it, or the negative log of that we want to minimize. And if it is a negative example, we want it to be close to 0. So this is the skip-gram model. And then, for all the words in my corpus, for each word, we look at all the context and then log of this probability of W context by the W center. This is what we want to maximize. Okay. And based on this, we can learn, we use standard gradient descent that you are all familiar with. We learn the parameters theta. So theta comprises of these two matrices, W and W prime. Okay, so there are certain efficiencies we'll not talk about. So any questions? Any questions? Is it clear to everybody? This is just an example. Suppose you have this sentence.
Hello, ma'am.
Yeah.
Ma'am, what is the need to compute softmax if you have to find the probability? Then why can't we
So
go for
because
any
how
other?
we do find what is probability? Probability distribution, you want to have a distribution on these V words, right? So you want to have
Yes.
P1, P2, PV, right? So you cannot directly, if you directly look at what you get from the network. So what does probability mean? It means the summation should be equal to 1.
Yes. So, ma'am,
And
actually,
each
my
of
doubt is,
let
yeah,
me
actually,
finish.
my doubt. Okay.
So you want each of the PIs to be between 0 and 1, right? So if you just let the network have some output, those output may not satisfy the constraints of a probability distribution. But softmax does, you can try to get the probabilities, but it may not exactly satisfy the constraint. So whatever value you get, softmax is a way of normalizing it to convert it into a probability distribution. Yeah, now you can ask your question.
Yeah. Let's take an example, ma'am. Like in a linear layer, I got some values. Let's say A, B, C, and D. That four values. And if I want to convert it into a probability, then there may be one case that I can get a probability of A as A divided by A plus B plus C plus D.
Right. So that is another way of
Yeah.
normalization. So
Yes.
if you have
And
this
in
4-class
softmax,
classification, let me explain. Yeah. So if you have this 4-class classification, whatever is your problem, you have some input and you have these 4 classes and you get the 4 values. So how do you convert into probability? One possibility is A by, so A by A plus B plus C plus D, A by S, right? B by S, C by S, D by S. This is one possibility. What softmax does is e to the power A divided by e to the power A plus e to the power B plus e to the power C plus e to the power D. This is a second possibility, right? So this also converts to a probability, but there are some problems. What if, A, B, C, D, some of them are negative? So if you just use A by A plus B plus C plus D, there is no guarantee that the probabilities will not be negative. Okay. If you
okay.
take e to the power A, then you can, make it always positive. Secondly, this type of, transformation magnifies the scores, right? So if you have 0.1, 0.2, 0.3, 0.4, right? If you use this, the probability of this will be 0.4. Whereas if you use softmax, this will be magnified. So this is just another transformation. This transformation makes sure that the values that you get are all positive, that all lie between 0 and 1. And it also magnifies, it magnifies the higher probabilities. So this is the transformation people use in practice. Other transformations are also possible. And this transformation is also good because, you can easily differentiate it. This function is, the differentiation is very simple.
Okay, ma'am. Thank you.
Okay. But there are, this is not the only way. You can use others, but, I just said that, they have their properties. Okay, any other question? anyway, so this is just an example of how skip. So do you know what is the meaning of Vampimuk? Have any of you come across this word? Yes or no?
No, ma'am.
But can you guess something about the word from the context?
Some furry animal, like
It's an animal.
Lec23.
You can guess something, even though it's actually not a, not a word which exists, right? But anyway, so given this word from the context, you can form the positive examples and take a sample of negative examples, right? So these are your positive examples, and out of many negative examples possible, you can choose a sample of negative examples. And from this, you set up the objectives and you can run this. And if you want to experiment with Word2Vec, the code, actually, this is a very simple function. The code of the original Word2Vec is available from this site. And also in this site, you will see that some corpus is available. So if you wish, you can train and you can work with the vectors. Now, something very interesting. Now, this Word2Vec vectors, people try to understand and analyze these vectors. And some very interesting observations. Take the vector of king. So subtract the vector of man, add the vector of woman. So these are vectors. So you can do vector subtraction, vector addition. And this resulting vector is very close or parallel to the vector of queen. This is the observation. Okay. So did you get it?
Yes, ma'am.
Yes, ma'am.
So it was found that this simple linear projection, it had this nice property that it could capture that king minus queen vector, the vector subtraction of king minus queen and man minus woman, these were parallel vectors. And if you do king minus man plus woman, the vector that you get is very close to the vector of queen. This was an observation. Similarly, if you look at the different countries and their capital towns, and if you learn these vectors by using Word2Vec on a large corpus, it was observed that China minus Beijing, Russia minus Moscow, India minus New Delhi, these vectors were almost parallel. Now, why word embedding is useful? So this is a very important thing, not just for NLP, but the idea that pre-training, an unsupervised learning of these representations gives you a good representation of the words, and that helps in many different tasks in NLP. And in fact, this was done in 2014 or 13 by Mikolov et al. So subsequently, it helped, this type of representation helped boost the performance of many NLP tasks. So the use of word representation, Word2Vec and beyond, they have become a key secret sauce for the success of many NLP systems. Across tasks, named entity recognition, part of speech tagging, parsing, etc. And this also has different principles. If you learn a good representation on a task A and use it on task B, it is one of the major tricks in the deep learning toolbox. You must have come across this sort of transfer learning also in computer vision. Have you? Have you come across this sort of use cases? For example, this ImageNet challenge. On this, people develop these different systems like VGGNet, ResNet, InceptionNet. So these networks, pre-trained on the huge ImageNet collection, would be used on other tasks in computer vision. Do you agree?
Yes, ma'am.
Now, what we are doing here, we are pre-training on a task of language modeling. The task of language modeling is a very nice task because you don't require any label data. You are just saying take a text, take one central word, take the context word, you get the training instances for free. And there is so much of text available. So you have a lot of data. And from that, you can pre-train and learn the representation. And this representation you can transfer to other tasks. Then there are other applications. You can take English representation and Hindi representation, Mandarin representation, and you can map it into a common space. So you can have a word language independent representation. So a cat in English and whatever it is Hindi meaning, Billy or in Beral in Bengali. So their vectors will come close. So you can look at some dictionary entries where you have a word in English and a word in Hindi. And if you try to now project the vector of Hindi into English or English into Hindi, so that these synonym words, their vectors are close together, you get a language independent representation. And even one can try to learn joint embedding of words in images. So you take cat, picture of a cat, and the word cat, and you want to have a common representation. So these are called multimodal representation. So these are also very useful for various applications. So with this, I will stop today, and we will again have the next class next week.
Thank you, ma'am.
Okay.
Thank you.
Okay. So thank you all. And if you have